Our objective in this video is to look at how a theory was developed in the early days of the science that we now call chemistry that explained actually three laws that were kind of mysteries to people. So remember, a law is something that describes, it's well known to be how things work, but there's no explanation for why they work that particular way until we come up with a theory, and a theory is a tested hypothesis. One of these two laws is called the law of definite proportions. So the idea of the law of definite proportions was that they were finding that if you had a compound that was made of two elements or more, if you took it apart and you could separate one element from the other element and weigh the two, the ratio of one of the elements' mass to the mass of the other element would always be the same within reason, within the precision that they had available. You would find the same ratio. It didn't matter where you did it or how many times you did it or how large or small the sample was. You always got the same ratio of one element's mass to the other element's mass. This is called the law of definite proportions because it's a definite proportion of one element to the other. So here's an example. If you had three different samples of the same compound made from sulfur and oxygen, let's use trial one as an example. Let's say you had 100 grams of this compound. We call them compound A. And you could take all the oxygen out that was in the compound, find out you had 49.98 grams of it. That means the rest would be sulfur, and then you could find a ratio of sulfur to oxygen mass. So let's say you took your 50.02 grams of sulfur and you divided that by your 49.98 grams of oxygen, you would come up with 1.001 grams of sulfur for every gram of oxygen. So that's the definite proportion. And if you do it for the next sample, you actually get the same number. 11.865 divided by 11.855 is 1.001. In the next sample, it's fewer significant figures, but it's the same ratio. And you could do this thousands of times, and you would find that this compound would always give you that same proportion of sulfur to oxygen mass, that definite proportion. Another law that was a mystery, that had no explanation, was the law of multiple proportions. This one's a little bit more sophisticated, and it relies on you having two different compounds. So if you have two compounds that were made of the same elements, you could find that definite proportion that we were talking about for the last law for one of the compounds, and then find it for the other compound. And then you take those two definite proportions and you find a ratio of them to each other, and that always turned out to be a ratio of small whole numbers. Here's an example. Compound A, the compound that we were just working with before, we saw that its sulfur to oxygen mass ratio was 1.001. Compound B is a different compound, but it's also made of sulfur and oxygen. Let's find its definite proportion of sulfur to oxygen mass. So we'll take the 40.08 grams of sulfur, we'll divide by 59.92 grams of oxygen, and the ratio that we'll get is 0.699. So that's its definite proportion. Now, if we take 1.001 and we divide it by 0.699, we get 1.50, which is pretty close to 3/2. That's a ratio of small whole numbers. A simple fourth grader fraction was always what they were getting. And it's not just these two compounds, it's all the compounds. It always turned out this way. And it doesn't matter if you do it the other way around, 0.699 over 1.001, well, that's about 2 over 3. You're always going to get a ratio of small whole numbers. There was no explanation for this until this guy came along, John Dalton. He was a high school teacher. He was really interested in weather. He studied gases because he was interested in weather. And he stumbles upon these laws, and he comes up with a hypothesis that might possibly explain it. It comes in a few postulates. Here's one of the postulates. Everything is made up of tiny indivisible particles called atoms. This has been so well accepted for so long that we just kind of accept it like this knowledge has always been there, but this was revolutionary for someone to have evidence for this. The idea of atoms had been around for a long time, but had never been really taken seriously until John Dalton gave him the credibility of this evidence. Atoms of one element, he proposed, are all identical to each other, but they're different from atoms of all the other elements. So every oxygen is the same as every other oxygen exactly. Every sulfur is the same as every other sulfur, but no oxygen is ever the same as a sulfur. So that's another one of his postulates. Atoms can't be created, they can't be destroyed, they can't be altered. So that means all the oxygens that have ever existed will always exist, and all the sulfurs that have ever existed will always continue to exist, and no oxygen will ever change into a sulfur or vice versa. Another one is that chemical compounds are just different arrangements of atoms. And then when a chemical change takes place, you're just taking the atoms that already exist and just rearranging them in a different way. So for example, our two compounds might be explained by one sulfur with 3 oxygens in one of the cases and one sulfur with 2 oxygens in the other case. The oxygens in both compounds are the same exact atoms, same kind of atoms, same weight, same everything the same, and the sulfurs are the same. They're just rearranged in different ways. This explains the law of conservation of mass. Imagine you had a Lego set and you built a creation and you weighed it, and then you took that creation completely apart and built a different creation out of the same Legos, and you weighed it. Of course they would weigh the same because you just used the same Legos. Atoms are like Legos in that way, that when a chemical change takes place, you're just reorganizing all the matter that already existed. This explains the law of definite proportions as well. Imagine that you have this sample, you have 3 samples here of the same compound. It consists of 1 sulfur to 2 oxygens. If we took a ratio of oxygen to sulfur masses, it would just be the ratio of what, for this sample, what 2 oxygen atoms weigh compared with what 1 sulfur weighs. So I'm just making up simple numbers. Let's say each oxygen weighs 1. That would be 2 on the top, 1 plus 1. And let's say every sulfur weighed 3. That ratio would be 2/3. If we broke down this compound, well, we'd have 1, 2, 3, 4, 5, 6 oxygens, which would weigh 6 if each one weighed 1. And we'd have 3 sulfurs, which would weigh 9 if each one weighed 3. Well, that's 2/3. And if we took this one, well, we'd have 2, 4, 6, 8, 10, 12 oxygen masses if every oxygen weighed 1, and 1, 2, 3, 4, 5, 6 times 3 would be 18 sulfur mass, and again, that just reduces to 2/3. And so that explains why no matter how big or small of a sample you have, you get that same definite proportion. It also explains the law of multiple proportions. Here's our 2 different compounds, let's say. For this one, your oxygen to sulfur ratio, mass ratio, is going to look like that. So, let's say that each oxygen weighed 1, that would be a 2/3. And for this compound, you're going to have 1, 2, 3 over 1. So that would be a 3/3 ratio. So if you took the ratio of oxygen mass to oxygen mass for the same sulfur mass, well, this would just be like a 2/3 divided by a 3/3. And the 3 masses of sulfur, whatever that mass is, would just cancel out, and there's your simple ratio, 2/3. And the 2/3 exists because of the fact that these things come in whole number units. There's no half of an oxygen atom or half of a sulfur. They always come in whole numbers. And that explains the law of multiple proportions. Since that all 3 of these laws that were mysteries were explained by this hypothesis, it was kind of automatically supported by evidence as soon as it came out, and very quickly it became a permanent part of our understanding of how the world works.